Hey everybody, Dr. A here, and in this video we are going to be providing some background information on torsional deformation. And the way we quantify torsional deformation is by what's called the angle of twist, okay? So let's get started. An internal torque moment, which we typically call capital T, in a shaft causes the cross section to rotate, or we put in parentheses twist, about its centroid. Now this is going to happen along the length of the shaft, okay? This rotation in the cross section is called the angle of twist, and we typically denote that by the Greek letter phi, P-H-I, phi, okay? So a couple of underlying assumptions. We're going to assume linear elastic material behavior, which by that default, we're also assuming no out of plane warping or bulging. So that means that cross sections remain planar, okay? And then radial lines within a cross section remain straight, but they do rotate, okay? So let's go ahead and write out along with a sketch what we're looking at, all right? So let's say that we have a circular cross section, and I'm going to see if I can draw that a little better for us. Circular cross section, there we go. Subject to some torque moment T, all right? So it's causing a twisting effect. And let's say that we have a radius R here. So when this thing twists, this radius will rotate to a new position. So we'll call this R. Now this angle right here, this angle through which the radius rotates is called your angle of twist, okay? Angle of twist. And it's a function of shaft length and location. Okay, so when basically what we have here is if you have a shaft that's maybe fixed on one end, okay, and free on the other, and you have a location variable x here, then phi will be a function of x. So we typically expressed as phi as a function of x, okay? And this would be if you also have a total shaft length of L, okay? So again, this is meant to be kind of like a three-dimensional sketch of a shaft with a circular cross section, all right? So what's the governing equation, all right? So here we go. The governing equation for a shaft with a circular cross section for angle of twist is the following. We're going to have, let's go to the next page. We're going to have phi equals the integral from 0 to L, t as a function of x over j as a function of x times g as a function of x dx. Okay, so what are all of these terms mean? Well, L is the shaft length. T as a function of x is the internal torque moment as a function of location x. J as a function of x is the polar moment of inertia, of course, as a function of location x. and G is a function of X is the shear modulus, or also called modulus of rigidity, as a function of X. Now, a lot of times, some or all of these terms will be constants over particular domains. And so a lot of times, you can pull out some or all of these outside of the integral. So this is the generic form of angle of twist if you have functions for any of these three terms. But if you don't have a function, if you have a bunch of constant terms, things can kind of pull out of the integral as appropriate. Okay, so I'll go ahead and write for T, J, and G, all constant over a length L, then this becomes phi equals TL over JG. And this is our very simple version of that equation. Now you may be wondering, okay, I see the T, I see the J, I see the G. These were here originally. Where's the L coming from? Well, remember, if all of these three terms are constant over a finite length L, you don't need the integral anymore. But this dx, since the integral is from 0 to L, the dx just becomes the L basically. You're integrating, upper limit minus lower limit, and the lower limit is a 0. So you just pop an L in here whenever all three of these come out to be constant. So so you're left with this very simple formula. Now, what if you have a segmented shaft? Okay, so for a segmented shaft with multiple segments, each having separate constant properties and loads, we can write this as a summation. We can say phi equals the summation as I goes from 1 to n of TL over JG sub I, okay? Where n equals the number of segments of the shaft. Now, those of you who are familiar with axial deformation and like an axially loaded bar, this theory parallels that, okay? This theory is very similar. It's analogous to our background on axially loaded bar deformation. So if you remember, for axial deformation of an axially loaded bar, we have deformation is equal to FL over AE. So there's a force component, there's a length component, a cross-section area component, and a material property component. Similar here, when you have a torque-loaded shaft, you have TL over JG. So you have a loading component T, a length component L, a cross-section area property, in this case it's polar moment of inertia J, and then a material property G. Okay, G is a material property. It's a property of the material the shaft is made out of, okay? Let me go ahead and make this G look more like a G. Right now it looks kind of like a 6, but it's a G, okay? So, and again, you can see this in many forms. The thing to keep in mind is knowing when certain things are constant on a given domain. You can pull terms out of the summation, similar to what I said earlier. When you have constant terms in the integral form, things can pull out of the integral if they're constant. And then, maybe you have J and G as constant, but T is a function of X, so that would stay in the integral. So it's problem dependent based on what's constant and what's not, but these are the governing equations for what you would deal with. And again, the summation version is for a segmented shaft, okay? So that's going to conclude this background information video on angle of twist, which is a type of torsional deformation. Please hit like and subscribe if you found this helpful. Thanks for watching.